Okay, let's go over what we did today in History of Math, where we're looking at Islamic arithmetic. So we know it was first done by the Hindu mathematicians around the year 500, came to Baghdad around the year 780 when Hindu astronomers came and showed the way they did astronomy, which included the way they did arithmetic. And straight away, the Islamic scholars picked up on this, and very soon, around 800, we know that Al-Khwarizmi wrote his book on arithmetic. His name, when translated to Latin, was Algorithm, and from this we get our modern word algorithm. And this just kind of emphasizes that arithmetic is simple mathematics, but it is, if we look at it from a computer science point of view, it's, we're looking at efficient algorithms to do jobs. So we've got to worry about how to represent numbers, because with the Indo-Arabic numbers, you could basically write down any number that you could possibly deal with. This is hard to do, for example, with the other systems, like, for example, the ancient Egyptians. To write the number 23, they would have written something like 2 hoops and then 3 kind of strokes like that. The ancient Greeks would have had a letter for 20 and a letter for 3, and then combine it together. The Muslims, before they picked up this system, used a similar system similar to the Greek system. So they would have had a letter for 20 and another letter for 3. So it's kind of really hard to do anything then with any like 3, 4, 5 digit numbers. Okay, so it's base 10, it's cipherized, so that means that all the units have got a symbol, and so that means to arithmetic, you really need to know well how to handle those symbols. And that's why when we're in primary school, we learn our 7 times tables and 8 times table. So we're really good at any kind of arithmetic, including just single digits. We know how to add and multiply them sort of straight away. Okay, we sort of know that off by heart. It's positional, and so, like you've got units, tens, hundreds, thousands, and you can use that positionality in your algorithms to make things efficient. So let's have a look at a problem. Now, for example, if I asked you to, multiply together 2 really big numbers, given a big enough piece of paper and a pen, you can sit down and so if they're n-digit numbers, you would need to do each single multiplication in a digit, so that would give you n lines, and then you would add up those n lines, and so you would get something like n squared sort of single digit computations in doing anything with like multiplication of 2 n-digit numbers. And so, because we use paper, that is means we have plenty of space. But back in the day, back around the year 800, paper wasn't available. That didn't come till around the year 950 or so. It came from China. Chinese invented paper. So they used something called a sandbox, which was just like what it sounds like. It's just a little box. It's got sand in it, and you can write in it with your finger, and it's very easy to scrub things out. So you can write digits and replace digits really efficiently, but you've got no memory. Okay, and so how did they do their computations that way? So let's have a look how they did with decimal arithmetic. So let's have, for example, let's have a look at how you would add two numbers. So for example, if we had 153 and 386, so what they would do then is they would go ahead and they would work from left to right. So they'd rub out the 1 and they'd add the 3 to the 1 and they'd get a 4. And then they would add the 8 to the 5. Well, actually, they're adding 8 to the 45, but they're adding 8 to the 5. So they get rid of the 5 and replace that with a 13. All right, so they're going to write a 53. And then finally, they add the 6 to the 9, 6 to the 3, and they're going to get a 9. Okay, so let's look at that in slow motion. So let's have a look at 847 plus 659. So they write their two numbers down and working from the left. So it turns out, and a lot of things when you're doing arithmetic, working from the left is kind of neater. You kind of don't have to worry so much about carrying things over. So here we go, we add the 6 to the 8, and we rub out the 8 and put in the 14. Okay, then we add the 5 to the 4, and we get 9. And then finally, we add the 7 to the 9 to get 16. Put down the 6, and then we have to add 1 to the 49 to get 50. And so we get 1506. Okay, subtraction is just the reverse process, right? We do 8 subtracted by 6 is 2. So that gets rid of the 6. Then we get the 5, subtract 5 from this. So we subtract 5 from the 24, we get 19. And then finally we subtract 9 from that. And so that turns a 7 to a 6. And we've got to take away 1 from the 9 to get 8 because 9 is greater than 7. So we get 186. If we look at halving now, halving wasn't actually thought of as a division. It was thought of as a special type of subtraction. And this is the one thing where they kind of worked from right to left. So let's say we want to halve 2,345. So first we halve 5, so we get 2.5. And now we see fractions for the first time. So a half is 30 because they didn't have decimal fractions yet. In fact, decimal fractions were an invention of the Arabic mathematicians, and that's why we call it the Hindu-Arabic number system, because they added in the decimal fractions, and you can write positional, you put a decimal point, then after that you got 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, etc. So people kept on inventing decimal fractions. I think it was first invented in around 950 by Euclides. But then it was invented, it never took off because people were just used to using base 60 fractions. And so around 1425, Al-Kashi actually reinvented decimal fractions and actually showed that all the arithmetic that you've done before can be done with decimal fractions quite easily, just like it was done like in the modern way that we would do it. But it was forgotten. It came to the West. Simon Stevan first invented it in the West. It got forgotten. Finally, John Napier reinvented it in the early 1600s when he was writing his log tables. And this is the impetus that needed. So to be able to use the log tables, use decimal fractions, and then after they saw that decimal fractions were kind of superior, we never looked back. Decimal fractions became the norm. But it took like 600 years for that to happen. Okay, let's have a look at multiplication. It's kind of like the first interesting thing, and it's the one where you really have to worry about the size in which you're doing things. So you want to do your multiplication, but you haven't got much memory, you haven't got much space, right, to write the thing down. So let's have a look at 847 times 659. So what you do is you write down 847 and then you put 659, you put the unit of the second digit below the first digit of the first number. Okay, and we're taking advantage of position, right? Because unit, the 9 and the 659 is a unit, the 8 and the 847 is 100, unit times 100 is going to be 100. And so when everything is lined up how it needs to be. Okay, so the first thing we're going to do is we're going to use up the 8 in the 847. So we're going to multiply 8 times the 6 down below. 8 times 6 is 48, so we write 48 up there in that position, and you see that it's like 100 times 100, so that's going to be written in the 10,000 spot, so that 8 is 80,000 and the 4 is 400,000. So 800 times 600 is 480,000, and it's in the right spot. Okay, then we go over and we do the 8 times the 5 times the next digit. 8 times 5 is 40, and so we add it to the 48, but since we went over, the 48 is now a 480, so we're adding 40 to 480, so we get 520. And then finally, we do the last digit 9, so we're doing 8 times 9 is 72, and we write the 72 there. So remember that 8, the 8 in blue there is not really there, right? It's in the number being multiplied, that it's actually 5,200. We add the 72 that to, we get 5272, and it doesn't matter that we overwritten the 8 because the 8 has been used up. It's done its job. Okay, and so then we're going to work on the next digit, which is the 4. So we slide the 6, we rub out the 659 and we put it one place over to the, move it one place to the right, because now the 4 is a 10. So the 4 times the 6 is a 10 times 100. That's going to be 1,000. So we've got to make sure things go in the right place. So the 4 times the 6 is a 24. We add it to the 27 that's there, so we get a 51. So everything is in its right place so that when you enter the number, it enters in the right place. Okay, the 4 times the 5 is a 20, and so you change the 2 to a 4, and then finally you do the 4 times the 9 is the 36. You add the 36 to the 24 there, you get 60. And now you've overwritten the 4, but everything is in its right place now. And so then you can go on to the last digit, which is the 7. Again, you move the 659 one place to the right because now you've got unit. Unit times 100 is going to be 100. 7 times 6 is going to be 42. So you add 42 to that place there. So 42 add to the 36 gives you the 78. The 7 times 5 is the 35. So you're going to add it to the 780. So you get 815. And then finally 7 times 9 is 63. You add that to the 157, you get 213. And you've done exactly the same computations that you did if you wrote it out the way you would do with the 3 lines and then adding them up. It's just that you've been as efficient as possible in using your space. Okay. Pretty, I think it's pretty neat. it really shows how much they understood this number system. They're using it to their full advantage. Of course, they completely didn't know it because they didn't have decimal fractions. But later we'll see how knowing this system it helps with other things as well. Okay, let's do division. Let's divide 5,625 divided by 243. So in this case, we do end up having to use 3 lines. So we do the 5,625, we put the 243 underneath it, so that the last digit 3 lines up with the 562 because 243 goes into 562. So that's why we put the number there. So we put it in the leftmost place such that the number above it contains the number below it, is greater than the number below it. So 243 goes into 562 twice. So we write the 2 up there. And it's in the 10 spot again because we're taking advantage of the positional system. We've got a number in the thousands divided by a number in the hundreds. The answer is going to be a number in the tens. So that 2 has to go in the 10 spot. We then take 243, we multiply it by 2, so that's 486, and we subtract it from the 5625. I'm missing out a few lines here because if you can take it slowly, right? You could do 2 times the 200, you could take that off. You could do it digit by digit, right? I'm just saving time here because I can see that I can just take away 486. So now I've got 765. I now move the number 243 one place to the right. So now 243 is less than 765. I divide 765 by 243. I see that it goes in 3 times. So my unit is 3. And then I take 3 times 243 and I subtract that from 765 and I get 36. So we see that our number is 23 remainder 36. Okay, great. Now, the problem is, what is 36 divided by 243? What I want to do is I want to convert it into a number that I can understand. So we're going to turn it into a fraction. It's going to be a base 60 fraction because they did base 60 fractions. Okay, so you've got to solve 36 divided by 243 equals x divided by 60. You want to find that digit x. Well, obviously what you do is you multiply by 60. It's kind of similar to find a percentage, you multiply a fraction by 100. Okay, that process is called raising. So 36 times 60 is 2,160. So you'd now do the division of 243 into 2,160. And we see that it goes 8 times. We take 8 times 243 and subtract that from 2,160, and we get 216. Okay, so we've got 8 remainder 216. So this is in the seconds. Okay, so we raise the 216 again. We multiply 216 by 60. And again, we divide 243 in it. We see that we put the 243 below the tens column, and we see that it goes in 5 times. So we've got 50. We take 5 times 243 and subtract that from 1296, and we get 81. So now we've got 810, and so we move the 243 once over. That 3 times 243 goes into 810 3 times, and we get a remainder of 81. So we've got 53 remainder 81. We raise the 81 again. We multiply 81 by 60. We get 4,860, and 243 goes into that perfectly 20 times. And so the answer we get is 23, 8 minutes, 53 seconds, and 20 thirds. So the nice thing about base 60 is it's a lot more divisible by other numbers, and so whereas it has less, it's got more terminating fractions than decimal does. I guess that is an advantage of it. Okay, let's take a break for a second while we switch to base 60.